everybody! Today I'll be demonstrating a wave tank. In this demonstration we'll be doing the double slit interference pattern and refraction. But first, let's start with refraction. When water waves hit shallow land, the waves slow down, which causes damage to coastal areas. We can see this with our demo when the straight waves hits the underwater surface. Speed is calculated by distance over time. We measured our distance to be 0.1 meters and used a stopwatch to calculate time for the initial depth to be roughly 0.61 seconds. And therefore our initial speed is 0.16 meters per second. For a second depth, the distance is the same, but time is roughly 0.83 seconds, resulting in a speed of 0.12 meters per second. It is important to note that there is a high uncertainty due to human error in the time calculations, but for our demonstrations, it serves the right purpose. Refraction is the change in direction of a wave as the depth changes. We can calculate this change in direction by manipulating Snell's law to better describe water waves. In Snell's law for light waves, n is the index refraction, calculated by dividing the speed of light in a vacuum with speed of light in a medium. For water waves, we'll be substituting c for the height of the initial depth and v for the height of each depth. Therefore, n will equal the initial height divided by the height of the next depth. In our example, the initial depth is 1 centimeter, and the depth of the water over the plastic piece is 0.3 centimeters, resulting in n equal 1 and n2 equals 3.3. Now that we know n, we can calculate the angle of refraction using Snell's law. Let's say our initial angle is 45 degrees. We can calculate the second angle of refraction by plugging the numbers in and solve for theta. In our example, the second demonstration I want to talk about is the double slit interference pattern. The double slit experiment can be shown by using 2 point sources attached to the wave generator and using a high volt pattern. Interference occurs when the two waves with the same frequency and constant phase difference make contact with each other. We can see that there are some areas with waves and some without. These are called fully constructive and fully deconstructive interference. During fully constructive interference, the two waves from the point source collide, resulting in a single wave with double the amplitude, causing a maximum. This is caused when the two waves are in phase. During fully deconstructive interference, the crest of one wave and the trough of the other wave overlap, resulting in the amplitude of the single wave to be less than the individual wave. If the peaks that are perpendicular to the point source are maximum, then the waves are in phase. Likewise, it's a minimum, then it's out of phase. Maximum and minimum peaks can be calculated by using Young's double slit, fully constructive and fully deconstructive interference conditions. First, we will calculate the fully constructive interference condition. D is the distance between the 2 point sources. Theta is the scattering angle. M is the order number for the perpendicular maximum, m equals 0. Lambda is the wavelength. For our example, the distance equals 6.1 centimeters. The wavelength is 2.1 centimeters. Using these measurements, we can calculate the fully constructive and fully deconstructive angles as per the different order numbers. Let's start with fully constructive interference. We can take the formula and arrange it to find the first order maxima scattering angle. This angle is the distance between the center of the 2 points sources and the first maxima, in our case, is 2.1 degrees. The second angle can be calculated similarly, where the angle from the center point is 43.5 degrees. Fully deconstructive interference is similar with one modification. You want to add a half to the order number. For fully deconstructive interference, we can use the same principle, but by adding half to the order number. For our number 0, we can calculate the scattering angle as 9.9 degrees, and so on for each order. For order number 1, we get 31.1 degrees, and 59.4 degrees for order number 2. Interference can only occur when waves from the source emit constant phase with respect to one another, as well as they have to have identical wavelength. Other fun physics demonstrations that can be done with a wave tank include reflection, diffraction, and Doppler effect. Thanks for watching!